Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science, and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay, good afternoon, everyone, and welcome to Topo Seminar. I don't know which number. Okay, 60. Okay, and today's speaker is Dr. Pongwit from IFTEP Laboratory. So, well, I would stand here. Okay, this is his topic. Is about something fancy, AdS propagators and celestial propagators. Sound interesting? Okay. Okay. If you are ready, please.
Yes. Thank you for the kind introduction. And today I'm going to talk in the topic of, as you may know already, from AdS propagator to celestial propagator. So the aim of this work is to build a dictionary between AdS propagator to celestial propagator to what is known as the celestial holography, by which I will introduce it later. So this is all the outline of this talk. So I will talking about the review of AdS CFT and then the celestial holography, and then I will tell you how to build the celestial amplitude, which is from the conformal primary wave function, and we use that conformal primary wave function in order to construct what is called the celestial amplitude. And if we know the formalism already, I will compute the celestial propagator in the massless case and in the massive case respectively, and then going to conclude my result. Okay, let's first talking about the AdS-CFT. As you may know, this is the holographic principle that relate to theory together. On one side, it is the gravitational theory in AdS space. On the boundary side, it is the quantum field theory and it is not the ordinary quantum field theory. It is the quantum field theory that enjoy conformal invariance, and this is the picture that show an example of conformal transformation, which is the transformation that it is the space-time transformation that leave the metric invariant up to the scaling. In short, it is the transformation that transform the space or the coordinate that preserve the angle of the coordinate itself. You can see that this is the 90-degree, the grid is 90 degrees, but if you going to transform it as this, it is also preserve the angle of the lines of the coordinate. So in this work, I will focus on the AdS space. It is the Euclidean AdS space. So this is the line element that I'm going to use. And I'm going to consider the massive scalar field in this kind of space. And this is the action. This is the action of the field theory of the massive scalar field. And as I said earlier, that the AdS allow you to consider the field in the bulk by the field on the boundary. And this is the relation that relates the field in the bulk to the field in the boundary, or maybe it's called the boundary data here. And the way to relate it is to introduce another object, which is called the bulk to boundary propagator. It is an object that connects, let's say it is the object that connects the boundary to the bulk. It translates the data from the boundary to the data in the bulk, or vice versa here. And this is the object that I will pay attention to here. In this work, I would try to translate this object into the celestial world that I'm going to give you more information about that next. And the form of the boundary propagator is in the equation 4 here. It is a well-known form here. It is a well-known form here, where Z and Z prime here, Z and Z prime here is the boundary coordinate, and Z0 here is the bulk coordinate. If from 0 to infinity, 0 means you are in the boundary, on the boundary, and infinity means you are probably in the center of the bulk. The data of the AdS space would be encoded into what is called the conformal weight or conformal dimension here, which is which give you this. It encodes all the information about the dimension of the space, and the L is related to the radius of the AdS space, or the curvature of the AdS space. And in this work, I'm not going to directly translate it into the celestial amplitude directly. What I'm going to translate it is the equation 5, which is called the boundary to boundary propagator. The idea of the boundary to boundary propagator is that you have the propagator on the boundary, which is labeled by 2 points x and y here. But the mechanic behind it is through the equation 5, is that you construct it using the boundary propagator, meet it at some point in the boundary, and then propagate it back to the boundary. And I will use the equation 5 here. And what I actually use here is the equation 6 here, which is I'm going to put everything in the equation 5, put the boundary propagator in equation 4 here, and use the Schwinger parametrization to rewrite it in terms of this kind of integral here at the starting point. Okay. So this is my starting point. meaning that I'm going to focus on this object equation 6 here, which is the boundary to boundary propagator, and I will map this propagator here onto the celestial space. Okay, but I'm not talking about what is the celestial holography or anything yet. So next, I need to review what is the celestial holography is. Okay. It turned out that this is another area that very fascinating in GR. In 1962, by this work, the BMS, Bondi, Messner, and Sachs, he discovered they discovered a striking result that for the asymptotically flat space, or we can say it AFS, asymptotically flat space, is enjoy the symmetry, not the Poincare symmetry, but it's an enhanced symmetry called the BMS symmetry. Okay, thinking about this, asymptotically flat space, meaning that if you look far enough, if you look far away enough, the space is approximately to be Minkowski space. And you know that the Minkowski space enjoy Poincare symmetry, right? You would expect that in this AFF space, in the limit that you are large, I mean your location is large enough, maybe you map, not map, you limit R going to infinity, you would expect that this asymptotically flat space would enjoy the Poincare symmetry as well, but it turned out that it's not. It enjoys much richer symmetry. It's called BMS symmetry. And here is the Minkowski metric in boundary coordinate that they use to consider. Here, okay, this is the Minkowski metric, where in boundary coordinate they parameterize coordinates, 4 coordinates as u, r, z, z bar. You can perceive u as a time variable coordinate, time-like coordinate, I mean time coordinate. And r is the spatial coordinate, so that in the AS space-time is reduced to this kind of Minkowski coordinate when you limit r go to infinity here. Okay. So what they show is that they try to solve this equation, not the equation, the approximately equation here, equation 8 here, that this is the Killing equation that determines what are the symmetry that give the metric invariant as r go to infinity. And it turned out that the symmetry it should be another slide. I'm not sure. It turned to black. Maybe it's mapped to the celestial sphere that we need to go to. Okay. So it turned out that the symmetry is called the BMS symmetry that gives the space, I mean the metric invariant at infinity. The BMS is, roughly speaking, it is the Lorentz invariant together with what is called the super translation, which is nothing to do with the super symmetry. It calls super because it is richer than than the actual translation. The translation is like the subset of this super translation. And this kind of super translation, it has, let's say it has infinitely many degrees of freedom, meaning that it has infinitely generator in order to generate this kind of super translation. Okay, and because we have symmetry, we can construct the Noether chart. The Noether chart Q can be constructed. Okay, if you construct the Noether chart in equation 9, you don't have to worry about much about math, but this what matters here is the function f here that depends on the it relates to the super translation here. Okay, and you know by the Noether chart, the chart is tell you the change of something, right? The change of something, and if this transformation is actually the symmetry of the space, it should not make the scattering matrix. It should make the scattering matrix invariant. So this is the form here. This is the constraint here, that because the idea is because this is the chart that is from the symmetry. If it is actually symmetry, it needs to form this let's say uniform this, which is called the Watt identity. It needs to be satisfied. And if you compute everything with the equation 9 and the scattering matrix that I'm not going to go into detail, it turns out that if you solving the equation 10, you give the equation 11. And the equation 11 here is a long known, it is a long known identity called the Wavefunctions theorem. Okay, it's known in the 1965 year, which is nothing. This Wavefunctions theorem here, soft theorem here, is nothing to do with the GR. It is all purely quantum field. Okay, the Wavefunctions theorem tell you that if you have the scattering amplitude, let's say you have the amplitude that involves n+1 particle. I write it n+1, which is n is called the hard particle. N hard particles with one soft particle. One soft particle meaning that the particle with very low energy here. And by very low energy, we parameterize at omega, where we limit omega to 0 here to represent the energy of the soft particle to be very, very low. And in particular, this soft energy is the photon here. And it turned out that by limiting this, it gives you the scattering amplitude of n-hard particle time with what is called the soft factor here. Okay, and plus the error function that at the error of order omega, because omega is small. Okay, this relation. Okay, let me tell you that the BMS symmetry is already known in 1962, and the Wavefunctions theorem is already known in 1965, but there are completely two different areas at that time. Until 2015, this work by this guy, these people here, they they will realize the connection between these two areas, the soft theorem and the asymptotically symmetry together. And this is a very fascinating diagram that found by Strominger in 2018. I mean, okay. This triangle is related to 3 different areas together. As you see, the first area is the asymptotic symmetry, and the soft theorem that I already discussed earlier. They are already related here. But another area, we call the memory effect, which is another different area in physics. But it is interesting that by studying the asymptotically flat symmetry, they allow us to relate 3 different categories of physics together. The first one, asymptotic symmetry, is related to GR. Soft theorem is related to the quantum field theory. As I shown here, it is discussed about what is the form of the scattering amplitude when one of these legs is solved. And another area is memory effect, is the area that deal with the observation, real observation. And as you can see here, if you remember this pattern here, do you know what kind of this pattern is here? I know it's not a lecture. Yeah. It's all correct. It is a gravitational wave or merging binary system together. It turned out that if the asymptotic symmetry is true, we can observe it via the gravitational wave detection, such that the memory effect, it tells you that before the gravitational wave occurs, if you have this kind of length here, if the gravitational wave encounter it, these 2 points would be wobble around, right? Because it fluctuates around here, it would be wobble around here. And then if the gravitational wave pass, the memory effect tell you that these 2 points will not be at the same length as before. This is called the memory effect. And how it relates to this kind of symmetry is that you because the symmetry tell you that you have the symmetry of the space-time, and the symmetry of the space-time relate to the vacuum of the space-time. And then this is somehow related to how you change the vacuum to another vacuum, meaning that if you perturb the system, with the gravitational wave, your vacuum before the gravitational wave will be different by the vacuum after the gravitational wave. Okay. Okay. Next, I'm going to talk about the celestial holography. In celestial holography, it is the conjecture that presented by this guy here. It tells you that we can match the 4D S matrix in asymptotically flat space-time to the 2D correlation function here. You may think of this. This is the Penrose diagram of the 4D Minkowski matrix here. Sorry, 4D Minkowski space-time here. And if you have this incoming particle and outgoing particle. Actually, this particle need to be massless because it can go to this boundary here. It needs to be massless. All of the data in the 4D can be encoded in the 2D sphere, and that sphere is called the celestial sphere. Something like this. Here, the outgoing particle and incoming particle. It's just a point on the sphere. Okay. Okay, and this is in 4D we have the Lorentz group, right? We have the Lorentz group, but in 2D we have the PSL2C group, which is the Mobius transformation group, and we know that it's locally isomorphic to each other. So that is the let's say the first hint that we can relate this theory together. But how can we actually construct the 4D S matrix and map into the 2D sphere? Okay, we map it via what is called the conformal primary wave function. Okay, and before we consider the primary wave function, we need to consider what are the data that go into embedded into the 2D. You know that because in 4D, all the data is in the momentum. You can see that, okay, if in 4D you have momentum K, and for the massless you can parameterize by giving it as omega times Q, where Q is a null vector, where omega you can think of it as energy. It is the energy of the particle here. And because it's null, you can parameterize it as here with the parameter Z and Z bar. Okay, with the parameter Z and Z bar here. And you may think the parameter Z and Z bar here is referred to the point in the sphere by maybe a stereographic projection or the similar sort here. So basically, as you can see here, all the information are encoded in Z and Z bar and omega as well. Okay, the information of the particle. That's why we can perceive it that as the incoming or the outgoing particle can be the information can be encoded in 2D because it can be parameterized to via Z and Z bar here. And equation 13 is the parameterization I can use for the massive particle. And for the massive particle, there is a parameter y. A parameter y here. The parameter y here is another parameter that it tells you about the bulk of the space, because the particle because the massive particle cannot reach the null infinity. It cannot reach the null infinity or the boundary of the asymptotically flat. We need to, it need to be inside the 4D space. It cannot reach the boundary. So that's why we have the y variable here. And we can construct the primary conformal wave function in equation 14 and 15. Equation 14 is for the massless field. Equation 15 is for the massive field. the massless field here is basically is that you map the parameter omega to another data which called h here, which is called the conformal dimension, which is called the conformal dimension. And the equation 15 here is the conformal primary wave function for the massive field. As I said earlier, because the field live on the bulk, it's not reach the boundary. So it is what is called the bulk to boundary propagator in order to map the bulk to the boundary. And this is the form of this function gh, which is it is called the bulk to boundary propagator. But this bulk to boundary propagator map means copy bulk to celestial propagator. It is not the same as bulk to boundary propagator I mentioned earlier in AdS. Okay, under the Mobius transformation, this primary wave function transform as primary function in conformal field theory. Okay, if you familiar with the conformal field theory, this is the basically the notion of the primary field or quasi-primary field, depending on the definition. And by this work, we can map the 4D amplitude into the what is called the celestial amplitude by using this propagator. Sorry, by using this primary wave function in order to transform this ordinary 4D amplitude into the 2D amplitude here. You can state the difference as not a capital A here is the in the Minkowski space, and the curly A here or the fancy A here is the amplitude in celestial space. And for the massless case, this transformation is known as the Mellin transformation. Okay, I know that there is a lot of information, so let me summarize the goal. The goal of this calculation is here, as I said here, I'm going to compute this for the propagator here. And in equation 19 here, this K delta here, it is the bound-to-boundary propagator in the AdS space. I would like to know if there is a resemblance, if there is a similar structure for this kind of AdS space here, if I transform the equation 9 using the transformation that I given to you earlier. Okay. So what I'm going to do is I'm going to transform equation 19 to the celestial amplitude, or in this case, the celestial propagator. And there are two cases, the massless case and the massive case. For the massless case, it is shown in equation 20. And for the massive case, it is shown in equation 21 here. Okay. Okay. So let's first compute the equation 20 first. Okay. And then after I finish the calculation, I will compare with the original propagator 19 and see what is the translation from the AdS propagator to the celestial propagator. That is the idea. Okay. Now I'm start with the equation 20. If you don't remember, it's fine. It's this all here is all math. Okay, it's not think about the concept that I already presented earlier. So I take the form of equation 6 and and substitute it into equation 20, and this is turned into the equation 23 here. And okay, sorry. What I need to the equation 20 turn into this, which is equation 24, where this k here, it is basically the Fourier transform of the propagator kx and y here. So I need to compute equation 23 first and then put this equation 23 back to the 24 here. By computing the equation 23, I need to basically to decompose this Dirac delta function. This Dirac delta function here is from, it is there because of the conservation of the momentum. Okay, and I decompose it as equation 25. Here, I mean, more information can be found in my paper. And after I use, okay, as you can see here, the delta function gives you the delta function of z minus z bar here. Okay, z minus z bar here. It means that these two guys here is 0. These two guys here is 0. And if I implementing this selective propagator turned into a very basic integration which gives you a constraint here. And this constraint is a known constraint for the in the selective space. It is relate conformal dimension together here. Okay, it's good that we can recover the known constraint, but I'm not get the structure of this propagator yet. So it would be more useful not directly implement this constraint at first. Okay, and because I would like to assimilate, or the fact that I would like to make the structure like the boundary propagator as shown in the equation 19 here. In the equation 19, you can see here there is two boundary propagator that join together, right? So in order to simulate this, I rewrite the Dirac delta function as equation 28 here. Basically, I separate the Dirac delta function into two parts, where I doing this because I would like the intermediate step that made the propagator to propagate from this point to this point, and then propagate later from this point to another point. That is the idea. So when I using the equation 28, this allow me to split the integrand into two parts. The first part is the function that from Z1 to Z, and the second part is from Z to Z2. Something like equation 29 here. And as I said again, all later on this is just math trick here that I'm going to evaluate the integral here. So first I need to integrate out the rho integral. By doing so, I reintroduce the variable into u and x here using this kind of variable change. Okay, and then I integrate out. Then after the redefinition of the variable after the change of variable, it turned into equation 31 here. As I said, I turn rho 1 and rho 2 into u and x. Then I integrate over u. Integrate over u out, give you equation 32. It gives you this, which is still messy. But if I use the condition that I provide you earlier, which is the celestial conformal constraint here, this equation 26 here, that h1 plus h2 need to be equal to 2. If I use this, it turns out that I can basically get rid of something, get rid of the exponent term here. And luckily, this integral turn into the known form, which is called the Feynman parametrization here. Equation 33, such that we can, all in all, such that we can reduce the integrand directly into two parts here, where this k delta here is basically equation 35, which is quite a clean form. So basically, if you compare the result that I already got 33 here and compare it with the equation 36 here, it share the similar structure here, even though it's on the different space. But you can see that there is a simple translation that you can translate directly the boundary in AdS space to the boundary propagator in the selective space of the massless case. Then directly, I mean, it's a bit hand-waving speaking, but what I can do is I can compare these two equations together and translate the AdS propagator to the selective propagator directly. Okay, next is a massive case. Okay, so my goal again is to compute the equation 38, which is here. If I substitute everything, for example, this the original boundary propagator k xy here. If I insert the equation 6 onto it and compute this, it is the Fourier transform of the boundary propagator, I got the equation 40. And then I need to take the equation 40 back to the equation 38. Okay? But before that, let me tell you the constraint first. Okay, if I apply the on-tail recursion relation, if I apply the on-tail relation such that the p square needs to be equal to 1, and after the long calculation, I would get the similar condition, but a little not similar. It is a different condition, which is h1 minus h2 need to be equal to 0, or I mean, it need to be equal to each other. h1 need to be equal to h2. Okay, again, what I do here is I need to construct a structure that relates to the original boundary propagator of the AdS-CFT. What I can do here is I'm going to use the conservation of momentum to rewrite this P1 square and P2 square as P1 dot P2 here, and as this kind of parametrization, and put it back to the equation 38, and it gives you this. Okay. In equation 38 here, I believe I already expand the radial function already. Okay, what I can do here is I integrate out y2 and w2 to get this kind of equation. And then what is left here is to get rid of the rho 1 and rho 2. And this rho 1 and rho 2 integral here is nothing but it gives you, it is in the form of the Bessel function here in the equation of in equation 45 here. Okay, and all in all, you can rewrite the equation. You can rewrite the massive selective propagator as in equation 46 here, where you can, okay, here. Okay, you can compute the equation, the celestial propagator at equation 46. Therefore, you can define the boundary propagator as equation 47, and then you can get the nicer form of the celestial propagator as in equation 48 here. And you can see it is this form is separate the propagator into two terms here, into two terms. Does that mean that we can translate directly the boundary, sorry, the AdS propagator to this celestial propagator? The answer is a little bit subtle. It's a little bit subtle. Let me revise. Let me update my result. I know it is a lot of calculation going on, so let me update what is the result I get. So after compute everything, I get equation 50 and equation 52 for the massless and massive case respectively. And you can see that the propagator factorized into two terms here with the intermediate step here. It's like, from the equation 50 is like you have the propagator from Z1 to Z, and then you propagate, you continue your propagation from Z to Z2 here. With this celestial propagator defined in equation 51. And for the massive case, you get the equation 52, where the K tilde here is equation 53. Why do I use tilde here? Because it's not because it's, we cannot compare it like, we cannot compare it piece by piece, because you can see that in massless case there is basically you have the delta function here, which gives you which is different from the massive case where there is no delta function here. So basically, the growing measure is different, but it turned out that we can relate 52 to 60. We can relate 52 to 60. Okay. And here is my discussion that we can. It is subtle or it is out of place to compare these two celestial propagators together, because there is a difference in measure. In the massless case, it is here, the measure involves the Dirac delta function, which is not there in the massive case. So basically, we cannot compare directly the k in the massless case with the k tilde in the massive case. But we observe that we treat this kind of Dirac delta function measure here by consider the asymptotic behavior of this bound-to-boundary propagator. Let me going back a little bit. You can see that in equation 53 here, there is this guy here, and this guy here in near boundary limit, which is y going to 0. I mean, if y 0, it is 0, right? But in the near boundary limit, if y 0, it is 0 everywhere except for the point of w equal to z, right? So in that point, in this limit, we can perceive that this function behaves like Dirac delta function, and in fact, if we do the near boundary expansion, it is exactly stated in equation 56 here, where you expand the variable y, and in this case, I approximate y approximately 0, which is near the boundary. Okay. So the first leading term is you get back the Dirac delta function. The subleading term is involved derivative of the Dirac delta function. Okay, and by using this, we may write the celestial propagator as a series, where you can consider it as a series of this kind of expansion. I don't know what it's called, but but okay, you can consider it as a series. But for simplicity, if I consider only the first term, which is you recover back the Dirac delta function here, and if you compute everything, you get this kind of propagator here, and this is likely not. It is just, let me say something. Let me say that this way. It is on the same structure of the massless case, such that this could allow us, similar to the massless case, this could allow us to translate AdS bound-to-boundary propagator to the bound-to-boundary propagator via this kind of translation. And as the caution, this is just basically the first leading term. I'm not going to discuss the sub-leading term. Okay, for the conclusion, in this work, I'm build up the dictionary that mapping the 5D AdS bound-to-boundary propagator to 2D celestial propagator in both massless case and massive case. For the massless case, the propagator reduced to two-dimensional boundary-to-boundary propagator on celestial sphere. It is boundary-to-boundary because, as I said, the massless field can reach the infinity boundary. Whereas in the massive case, you have the bound-to-boundary propagator because the field cannot reach to the boundary. you need the propagator that grab the information from the box to the boundary. And the AdS data here, delta here, is embedded into the selector propagator in here and here. And if you like to know the form, you need to go back. Something like here. It's embedded into the AdS data. Is embedded into this let's say into the celestial world. And I think that's all for the talk. If you have any problems, feel free to not ask. Okay, feel free to ask. Sorry. Yeah. I think if you can get the idea of this paper, this is fine. The idea is I try to map the boundary to boundary propagator info into the celestial space, and I try to mimic the structure of the boundary to boundary. Okay, something like this. I'm start from this boundary to boundary propagator in the 4D, where this is constructed from the AdS3. But I map this to the celestial propagator in two cases here, and I try to compute in the way that it would mimic this kind of structure. This kind of structure means that you have the two propagators that going up at some point here. So so my idea is I try to find a probability function. Yeah. The one thing is the propagator is it could be the building block to build another thing, right? So we can start from that because we know that we can if we know the propagator, we can know a lot of things out of propagator. And another thing is I would like to know how the AdS data would be encoded in the celestial data, in the celestial world, because I try to relate to duality together, the AdS CFT duality and the celestial duality. The AdS CFT is AdS on the and let's say for 4D CFT, and then I assume that the 4D CFT it can be mapped into the celestial space by the celestial holography, such that in this work I try to see how the data in AdS space represent in the celestial world.
I don't get the idea of the relation between AdS CFT you mentioned about
the idea is kind of simple. Is that on the celestial holography, it tells you that you you can consider 4D, let's say 4D scattering matrix to the 2D correlation, right? And in 4D, you can use the AdS CFT let's say to construct the same scattering amplitude in 4D. For the let's say that in one side, we have AdS, and which is I call it AdS 5 as a 4D CFT. Right. Which is, I assume it to be flat. Then I would send the 4D so the idea is simple, is that because the celestial holography is mapped everything in here to the 2D celestial conformal field theory, but in 4D here, I can also relate to the ADF-CFT in this picture as well, and assume that this is, let's say, in flat. As well. So I basically relate directly this to this and this to the celestial sphere. That is the main idea.
Okay, let me ask something. So, in this case, this means that the boundary of the AdS is the fat space or asymptotically fat.
Yeah, I assume that.
Yeah, okay. But in the AdS space, in the boundary, it should be AdS, asymptotically AdS. I think it's, I just wonder why you consider it as the fat.
So I believe that generally speaking, the ADF-CFT is that you consider the gravitational theory with the non-gravitational theory, which is nothing to do with the gravity. For example, the quantum field theory that probably, let's say, the world of all of the quantum field theory, say. And the world of quantum field theory, we usually construct everything in flat space. So that is how I perceive it in that way.
Another question. So can you go to the conclusion slide? Or yes.
Conclusion, right?
Yes. Okay. Okay. From the last bullet. So in the massive case, you mentioned about they don't have the translation to a celestial like a boundary to the boundary propagator or.
I conclude that we need to work it more as I said in here, the structure is about the same except for this gluing condition here. So if I need the same gluing condition, I need to work a little bit on this kind of propagator here, such that I would expand this. I would expand this in near boundary expansion, such that I would recover the same gluing condition, such that I can say that, okay, if you have the same gluing condition, so basically you have the same object in the massive level.
Don't look at me.
It imply that we cannot encode the AdS data from massive case to the celestial world or not.
You can, if I answer it abruptly, you can, but you need to be, I mean, if you translate let's say if you translate if you translate the AdS propagator directly to here, you need to translate the gluing condition as well into here. But if you do the same to the massive case, you get it would not suitable because in the massive case you don't have the same gluing condition. If you would like to have the same gluing condition, you need to work more on this. That I can say.
Oh, thank you.
Okay, then Bart, please.
For in the BMS symmetry, so it's his symmetry for asymptotically flat space time, right?
Yes.
And the Minkowski space is I believe is asymptotically flat space time itself. So does it also have a BMS symmetry?
Frankly speaking, I think the actual Minkowski space is okay. The Minkowski space is a subset of the AFS, but let me say that the Minkowski space have the Poincare symmetry, but the AFS has more symmetry than Poincare, which is when I say more, it's infinitely more.
Okay. So I'm thinking that does it mean that the super translations depends on what the bound what the bound space time is?
I think the work that they do, it is the more general case of the asymptotically flat space. They try to make it as general as possible. So they, apart from this is the Minkowski metric here, but in their work, they add the sub-leading term that is probably in terms of R and 1 over R, 1 over R squared, something like that, consider as the sub-leading term that deviate from the Minkowski space. But if you when you consider R going to infinity, that sub-leading term is basically meaningless, something like that. And that, as general as possible metric here, they derive that a set of transformation possible is BMS.
Okay. And for the super translations, are they considered global or local symmetries?
Local.
Local.
Uh, hmm. Uh, but, mm, not to be honest, I'm not sure. But, I think it's local in the sense that the function f can be anything here. The function f can be anything here if you consider it as the power series expansion here or the Lorentz series expansion. I mean, the global symmetry is some part of it that define globally, but the function here is not necessarily. To answer your question, I think it's local.
Okay, but if it's local, then maybe we would expect that the neutral charge vanish. I don't know. I mean, not normally for local symmetry, neutral charge would vanish.
Okay.
Yeah, maybe we can try to
I
discuss.
will discuss this later.
And in your equation 55, so you mean you expect? Next,
55.
yes. So you mean you expect that in the limit y goes to 0, you get delta function,
Yes.
and have you checked it with like multiplying by test function and integrate?
Yes.
Oh,
That
okay.
that's how I get this
Okay.
this linear. Not linear. This kind of expansion.
Yeah,
That
but,
I'm use the Taylor series that expand in terms of y and multiply with this.
yeah, but it's,
Yes.
but it look a bit scary that subleading terms you have something that is worse than delta function. But
So
it's going to be
something-
a problem. I mean, you have got like derivative of delta functions.
Yes, that's why I don't consider it.
Thank you.
Okay. Anyone else would like to ask questions? Questions? If not, no, okay. Let's thank Ajahn Pongwit again for very interesting talk. Okay. And before we stop session today, just if people online come across this kind of video later, if you like it, if you love it, please share to your friends and don't forget to subscribe Eve channel. We have a lot of content, interesting content to come, right? Okay. Thank you very much for today. Bye.